Well, welcome, ladies and gentlemen. Today we're going to really start delving into the biochemistry, organic chemistry portion of this particular unit. And in order to do that, we really need to start with just some basics to organic chemistry. So when we talk about organic compounds, we're talking about carbon-based compounds. And really, all living things ultimately their chemistry is based mostly on carbon atoms. So hopefully you recognize this picture here. This is your carbon cycle. And really the vast majority of processes that living things go through are set up in our ecosystems to cycle carbon throughout that ecosystem. So things like cellular respiration, decay, photosynthesis, and then even things that we do in terms of burning things like fossil fuels ultimately cycles this carbon throughout our ecosystem. Initially comes in via CO2 and help from the sun via photosynthesis. Plants sequester that carbon along with energy, which then can either decay and end up in things like our soils, or oftentimes we talk about just that short-term carbon cycle where animals are then eating those plants, going through a process called cellular respiration, taking that carbon in as things like glucose and sugars, and then breathing the CO2 out, and this whole process continues. So, while carbon is going to be our big molecule, or big element that's going to support all of these organic compounds we're going to be talking about over the next couple of classes, there are other elements, all right, that are also essential to life, and we talked about these way back at the beginning of this unit. So remember that you need to be responsible for knowing not only carbon, but your hydrogen, oxygen, nitrogen, sulfur, and phosphorus as well. And these are going to be the major common elements that we're going to see as we move through some of these major types of molecules that make up living things. Now we're talking organic compounds, so by definition, an organic compound not only contains carbon, but also contains hydrogen as well. So we have to include both carbon and hydrogen to consider a compound organic, although there's millions of organic compounds that exist here on Earth. And in fact, more than 90% of all known compounds here on Earth are made of carbon. Part of why, if you've ever heard that term maybe in science fiction, were carbon-based life forms, well, because carbon really does form the basis to all of our chemistry. Now, if I'm an inorganic compound, there's plenty of those that also exist, but an inorganic compound does not contain both carbon and hydrogen. And just because we're talking about organic and being associated with living things, keep in mind that there are plenty of inorganic compounds that also are necessary for living things to function. Alright, they just don't contain both the carbon and the hydrogen. Example, water. We just spent copious amounts of time talking about all the important things that water does for living organisms, and yet water is, by definition, an inorganic compound. It contains the hydrogen, right, H2O, but I'm missing the carbon. Another major molecule that's part of that carbon cycle we just talked about is carbon dioxide. But carbon dioxide also an inorganic molecule. It's got the carbon, but it's missing the hydrogen. So just be careful. A lot of times kids will think organic and automatically jump to living, inorganic, non-living, and that's not necessarily true. Alright, it's just based on whether or not the carbon and hydrogen are both present or not. So, why are we carbon-based life forms? Why is carbon, of all the elements on the periodic table, one that ends up being this basis for the molecules that we see in living things? And this really comes down to several properties of carbon itself. One of which is the fact that carbon is what we call tetravalent, or has 4 valence electrons, and as a result can make up to 4 covalent bonds, not only with itself, but then also with other elements on the periodic table as well. And remember, of all the bonds that we talked about, covalent bonds are one of the most strong and stable bonds that we know of. So carbon's tetravalence allows it to make all sorts of variations on these things we talk about as carbon skeletons. Alright, so they can form carbon-to-carbon bonds, and we can get them to go in straight chains, branched chains, rings. These rings and chains can be almost an endless number of carbons long. We can get double bonds in these chains. So we really end up with this huge diversity, not just of these carbon backbones or carbon skeletons, but then you start adding different things onto those carbon skeletons and we get an even bigger diversity in the molecules that we are capable of creating. So let's start with the most simplistic of those types of carbon-based molecules, and those are your hydrocarbons. So hydrogen and carbon. So by definition, this truly is the minimum that we need to meet to be considered an organic molecule. In terms of living organisms, we don't see hydrocarbons very commonly in and of themselves, but that being said, we definitely see regions of molecules, things like fatty acids and our lipids, that are hydrocarbons. So, some properties we should know about hydrocarbons: well, they're nonpolar, alright, which is also going to then make them hydrophobic, so they don't readily dissolve in water. But we get them to interact and go through chemical reactions, and they are going to release super large amounts of energy. Part of why if your body breaks down fats, you're going to actually release more energy than you would if you were breaking down something like a sugar, alright, or a carbohydrate. It's also why they are our main fuel source in our vehicles, in our homes. Alright, here's diesel fuel. It's 14 carbons long plus 30 hydrogens. We put this in our cars, we burn them, and we get crazy amounts of energy out of them to drive our cars. So, when we're classifying and looking at properties of hydrocarbons, it's really based on two major factors: the number of carbon atoms that I have in that hydrocarbon, as well as how the atoms and carbon atoms, other atoms, end up arranging themselves. So let's take some time to explore those factors a little bit further. One of the things that we're going to practice today is drawing some of what these hydrocarbon skeletons are going to look like. And in order to do that, we have to understand some basic naming conventions that organic chemists use. So while these terms may not necessarily make sense to you immediately, we'll come back to them. But something we should understand: if I've got a compound name that ends in A-N-E, first off, it's going to tell me that it's a saturated hydrocarbon, and we'll go into what that means in a little bit. But essentially, it's like talking about a saturated solution, so I've got the maximum number of hydrogens I can produce in order to make that work. That means I'm going to have to produce strictly carbon-to-carbon single bonds. Alkenes, ENEs, are unsaturated, so there's going to be less than the maximum number of hydrogens for the number of carbons I've got present, and that means double bonds are going to have to be present in these guys. Alkynes, YNEs, also unsaturated, so less than the maximum number of hydrogens, and they accomplish that less than the max because of triple bonding between their carbons. So these are all going to be suffixes or ends of names that are going to give us some idea as to what's going on between the carbon bonds that are being formed in our carbon skeletons in these compounds. Some other naming conventions to know are the prefixes. Once we get up to a chain that has at least 5 carbons, then it's going to follow those sort of traditional prefixes you probably learned in math class somewhere along the way. Pent for 5, like a pentagon. Octagon has 8, so on and so forth. But below that, we've got some very specific organic chemistry prefixes. If we're talking a single carbon in a chain, then we use the prefix meth. Eth, like ethanol, is 2 carbon. Prop, like propanol or propane, has 3 carbons. Bute, if you've ever heard of a butane torch, the molecule we're burning there has 4 carbons. If the carbon skeleton itself is bent into a ring structure, then you'll often see cyclo out in front. And if there's some sort of branch coming off the chain, so rather than it being just completely linear, there's branches, you may see that prefix iso as well. So let's talk strictly saturated hydrocarbons for now. And we've seen that term saturated when we talked about solutions, right? It was the maximum number of solute particles I could dissolve in a solvent. Well, similar idea here in terms of that maximum, but now I'm talking about hydrocarbon chains. How many carbons are in my chain and how many hydrogens or bonds am I capable of producing off of that carbon chain based on the number of carbons there. So I'm maxing it out. And in order to have the maximum possible number of bonds coming off those carbons, that means that carbon has to form 4 bonds, and so every bond between one carbon to the next can only be a single bond, right, or a single shared pair of electrons. So these are your alkanes. Okay, so suffix-wise, we're going to see ENEs at the end of their compounds. But regardless of our carbons, they can be in straight chains, but they can also branch off of each other. They can still be in rings. Only difference here is that between every carbon, there's only a single bond. So here are just some examples, right? So here you can take a look at all the names. They all end in ANE. And between every carbon that's in these molecules, there's only a single bond between them, which is what's going to allow me to make the maximum number of hydrogens come off those carbons, because the rest of the bonds then have to be taken up by hydrogens. But that being said, I can make branched chains, so here's an example of that, isobutane. Alright, we can also bend them back into rings as well, but that big characteristic is maximum number of hydrogens because the carbons only have a single bond between them. So we're going to spend a little bit of time doing some practice with drawing out these types of compounds and just sort of looking at how their structural formula works. So let's take some time and do some practice with these. Alright, so we're going to start with some simple ones first. So here's where understanding those prefixes really is going to come into play. Alright. But if I take a look, all these guys end in A and E's, which tells me that I'm dealing with a saturated hydrocarbon, and so all of my carbon-to-carbon bonds are going to be singles. Alright, so first off I need to determine, well, how many carbons am I actually dealing with, and that's where that prefix is going to come in. So if I take a look at a pent, well, pent, hopefully we know what that prefix means, so I'm dealing with 5 carbons. Okay. So once I've determined how many carbons I'm dealing with, then I want to know, well, if I'm dealing with a saturated hydrocarbon, how many hydrogens does that mean I have? So I've got this really simple formula up here, and that's going to be what's used to determine the number of hydrogens I should have once I actually start drawing out that structural formula. So if I've got 5 carbons times 2, alright, so 5 carbons times 2, that's going to give me 10, plus I need to take 10 plus 2 additional carbons. Alright, so I end up with a total of 12 hydrogens in this particular molecule. So drawing out the structural formula, it's going to look something like this. Alright, so I need to do my 5 carbons, so 1, 2, 3, 4, and 5. Now carbon has to make 4 bonds, so currently I've got 1 here, 1 here, 3, and then my 4th is connected to the next carbon. Next one has 1 and 1, and then there's 2 connecting the carbons on either side of it. Same deal here, here, and then I've got 3 on the end. And each of those bonds then is going to get connected to a bunch of hydrogen molecules, or hydrogen atoms, I should say. And if I've done this correctly, I should end up with 12 hydrogens and 5 carbons. So let's double check and make sure that works. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens, and 1, 2, 3, 4, and 5 carbons. So good. We've done what we needed to accomplish that one. If I go down to the next one, now I'm talking hexane. So hex, what does that mean? Well, hopefully we know that means 6. Alright, if I do my math, how many hydrogens do I need? Well, 6 times 2 gives me 12, plus 2 more, I've got 14. I'm going to draw out the same molecule here, alright, and fill it up with hydrogens. So do yourself a favor, pause the video, and try the rest of the structures in this particular table, and then come back to the video and double check your answers and see how you did. Alright, so hopefully when you finished all of this, you were able to figure out that hep means 7, which means you should have a total of 16 carbons, and so your molecule or structural formula should look like this. And F, this is one that's specific to chemistry. It means 2 carbons, so 6 total, and so your structural formula should look something like this. We can also do this with ring structures. So if I'm talking about a saturated hydrocarbon that's got that cyclo out in front, right, that tells me that there's some sort of ring structure. The A and E still tells me that I'm dealing carbon-to-carbon single bonds. And so now the question becomes, well, what does the structural formula of these guys look like? So I gave you some rules for drawing these out down here. Alright, we're still going to need to determine the number of carbons I'm dealing with, and now that prefix typically is shoved here in the middle of the molecule name, and then I can use these basic hydrocarbon shapes as a way to determine that. So let's go over some examples with this. Alright, so if we take a look at this first one, so remember that ane tells me carbon-to-carbon single bonds, cyclo tells me it's now a ring structure, so I need to know what that hex here in the middle means, and hex means 6. So that means I've got a 6-membered hydrocarbon ring. So if I come over to this particular table here, it tells me I'm looking at the basic shape that looks like this. Okay? And at each of these points in this structure is where those carbons are going to end up. So if I draw out that cyclohexane, alright, I'm going to look something like this. So here's carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and then carbon 6. Alright? And then I've got to add those hydrogens. So remember that carbons have to make a total of 4 bonds. Well, right now, everybody in this ring is already making 2 bonds. So that means that I have to add 2 additional bonds to each carbon to satisfy its tetravalent ability. Alright, and coming off of those hydrogens, or off those carbons, I should say, are the hydrogens themselves. And so this is what we would see with cyclohexane. Alright, it would look something along those lines. Okay, so what if I talk cyclobutane instead? Okay, well, cyclo again tells me I've got a ring, ane tells me carbon-to-carbon double bonds, so I've got to know what that bute means. In this case, bute means 4. Okay, so come back over here to this shape. I've got a 4-member ring. It's going to look like a square. Each of those points gives me a carbon, so if I draw this out, I'm looking at something that looks like this, right, in terms of my carbon structure. But once again, remember, I've got to add in my hydrogens. Every carbon in the ring is already making 2 bonds, so I've got to add 2 more. And then fill those guys in with those hydrogens. Okay. So pause the video again and go ahead and finish up those last 2 and then come back and double check your answers. Alright, so hopefully checking out the answers, the structures that you drew, hopefully you came up with something that looks like these 2. Alright, pent means 5, so 5-member ring with carbons, 2 hydrogens coming off of each. And prop means 3, and so you end up with a structure that looks like this.